This video will be on section 5.1, the antiderivative. So the main topics in here, we'll talk about what the antiderivative is, and then the formulas that go for it. The formulas we'll see come from the formulas for derivative, because we'll see what the antiderivative is asking. It's very similarly related. Then we'll be computing general antiderivatives, and then building on that, computing specific antiderivatives. All right, but before we get there, to explain what any of those mean, what is an antiderivative? Well, ultimately what it is, by it, kind of like by its name, you might be able to figure it out, but the idea of antiderivatives is doing derivatives in reverse. Right, so think back to any derivative you've done, but instead of starting with the function and getting to the derivative, maybe now what's going to happen is you can think about it as starting with the derivative. We want to get back to the regular function. So in general, we could say get back to f of x from f prime of x. That's what we're going to be trying to do. Now the formal definition is exactly that. It says, suppose f is a continuous function. That means when you draw the graph, there's no breaks in it. Then the antiderivative of f, denoted g, is a function such that g prime of x equals f of x. Now all this is saying right here is exactly what I wrote in orange. So it's the function that, when you take its derivative, you get back to the answer. So it's better to think about it this way. We're trying to get back to f of x from f prime of x. Now the notation is something you'll get familiar with in this chapter. Writing do the antiderivative is written like this. So it says computing the antiderivative of f is often written like this. This is the normal notation. This long looking S sign is called the indefinite integral sign. If you have some fancy calculators, you'll probably see that integral sign on there somewhere. The inside, the f of x, that's the function that you want to find the antiderivative of. And then the last part, the dx, it's sort of like when we do the derivative and we would write d over dx. The dx is telling us what variable to do the derivative with respect to, and the same idea here, but it's the antiderivative instead of the derivative. And you'll find as I go through problems, and this is very standard, we don't really ever say do the antiderivative, not that it doesn't make sense, but often it's just easier to say do the integral instead of do the antiderivative because it's quicker to say, but they mean the same thing. All right, so this first example here isn't actually work that you necessarily need to write down, but I like to explain there's a little something extra when you do antiderivatives compared to derivatives, and this example will explain it. Okay, so I'm just going to read through this. It's before we write down formulas for everything, let's pose the question. What is the antiderivative of the function x? Meaning, what function, if we did its derivative, would get back to x? Well, the way we would write this is compute the integral of x dx, because that's our variable x. All right, so just to correspond everything here, the question, what is the antiderivative of the function x? Written in symbols means exactly this. So then this is what you'd see in the homework or a quiz or test or anything. And because of how I know and we know the power rule works, we can kind of guess at it. Don't worry, there will be formulas for, but just for now, I'm just kind of throwing the answer out there. the function y equals x squared over 2. If you do the derivative of x squared over 2, we know we would bring the power 2 down, we would subtract 1 from the power, and the 2's would cancel. So the derivative of x squared over 2 is x, and that means x squared over 2 is an antiderivative of x because its derivative matches the inside. All right, so once again, we're trying to take the derivative that we're given, f prime of x, and get back to the original function, f of x. All right, so we're given x, we're given f prime of x, we want f of x in the example here, telling you that the derivative is x. What is the original function? All right, so x squared over 2 is an antiderivative. But notice I didn't say the antiderivative because there are actually many, and to be exact, there are infinitely many answers, because anytime you do the derivative of a number, it's 0. So if we add on any number to our antiderivative, x squared over 2, and of course adding on negative numbers, so subtracting works just fine, still has derivative x. So for example, not only is x squared over 2 an antiderivative, x squared over 2 plus 1 is, x squared over 2 plus 2 is, x squared over 2 minus 1 is, and any number in between, fractions, decimals, pi, e, literally any number. Because when we do the derivative of those, that just goes away. So that is why we're going to have something in our formulas that you cannot forget when you do the antiderivative of, and that is this plus c. So it says if g of x is an antiderivative of f of x, then for any constant c, the antiderivative of f of x equals that g of x plus c. So in our previous example, we had f of x was equal to x. That was the thing we wanted to find the derivative of, or antiderivative of. G of x, the example we saw without anything added on to it at the end, was x squared over 2. So the way we would actually answer this question, the antiderivative of x, dx, equals x squared over 2 plus c. Right, but very important that you add on this plus c. If you don't add on this plus c, technically you do definitely have some work here to figure out x squared over 2, which we'll see below with the formula. It's going to be called the power rule for antiderivative. But if you don't include that plus c, there's quite a few problems that you won't be able to do because at some point you might need to solve for c. So it's really, really important, but also, it's part of the answer. Very important. To always add plus c when the act of doing an integral is called integrating. So it's always important to add a plus c when you integrate. We won't see until section 5.5 when you don't actually add the plus c, but it takes on a different form. So for now, until we get there, we will be adding on a plus c every time. Right. All right, so pretty much all these integral rules, there are all the derivative rules that don't include things like the power rule or the quotient rule or the chain rule. So they're the equivalent ones. Right? It is a lot at once, but the point is that because we've learned those we've learned the regular derivative rules, the antiderivative rules are very similar in nature. Right, so the first one, I'm going to number these so I can refer to them in a section. The first one says if you want to integrate some number times a function, you can factor the number out. That's exactly the same as derivatives. So factor numbers out. Now, of course, if it's just a number, that's not quite exactly the same because it has to be a number times a function. But that's what the first one says, factor numbers out. The second one says if you have two separate terms or more linked by pluses or minuses, you can integrate each part. And that's also the same as derivatives. Right, so remember way back when we started doing derivatives and we were just learning the very beginning rules, the power rule. Anytime we had more than one term, we did the derivative, we wrote it out to do the derivative of each part. And anytime we had a number in front of the power, we factored it out. It's going to work the same way here. Also back in the power rule, when we dealt with that, is we were learning, kind of two special rules that don't seem like they get captured by the power rule, even though they will. This first one is the same way. You can use the power rule for it, but it's easiest just to realize it in a slightly different way. So this says if you integrate just a number, then the answer is that number times x plus c. Right, but of course, when you integrate just that number, you have to get that number out. So when we integrate 3, for example, we would get 3 times x plus c. The c is got to be c. It's not an actual number that we're going to put in, but the number we're given in the problem, we have to make sure we keep that the same. All right, number 4 is the power rule for antiderivatives, for integrals, whichever one you'd like to call it. It says if you integrate x to a power, we kind of do the power rule for derivatives in reverse. We add 1 to the power and divide by that new power. Right. Now that's very similar to our power rule, but in reverse for the derivatives. For the derivatives, we multiplied by the original power, and then we subtracted 1 from the power. To reverse that, we have to also do them in reverse order. We add 1 to the power and then divide by that new power. Right, so the biggest mistake here is not necessarily forgetting to add 1 to the power, it's not dividing by the new power. It's usually what I see. So you have to make sure you change the power first. This little thing here that says if n is not equal to -1, this will be covered in Rule 6. Now the reason why n cannot be -1 and this can't work in general is because if n is -1, then you end up dividing by 0, which is bad. But when n is -1, you'll have a very familiar function that you know what that derivative is already. Right. Rule 5 says the integral of e to the x dx equals e to the x plus c. Same deal for derivatives. When you do the derivative of e to the x, it's the same thing. So when you reverse it, you still get the same thing, but you have to remember that plus c. And then the last one, like I said, this is when you integrate 1 over x, n being -1, x to the -1 power is the same thing as 1 over x. And I'll just go ahead and point that out. That's always nice to point out. That's why we have a separate rule. The reason we can use a separate rule here is not necessarily because we get 0 for the power. It is more so because what function's derivative is 1 over x? Well, it's the natural log of x. So when you integrate 1 over x, or x to the negative 1 power, you get the natural log, but a little extra thing here is you get the absolute value of x when you integrate it. This is because the domain of 1 over x, if you want an explanation, is everything but 0. We can plug in negative numbers. Negative 1, if we plug that in, we get 1 over negative 1, which is negative 1. The natural log, you cannot plug in negative numbers, and this is the fix. So in general, we can't plug in a negative 1 for the natural log, but if we have absolute value around it, then the natural log of absolute value of negative 1, well, the absolute value of negative 1 becomes positive 1, so we can actually figure that out. But that's going to be a big thing that's easy to forget, is the absolute value. Right, so the one thing it might seem like we skipped is integrating the natural log of x, but this is our natural log antiderivative rule. You need a special rule that we don't do in this class to integrate it. So we will never integrate the natural log of x by itself. You might see it in some problems in future sections because we will have the equivalent of the chain rule. That will be our only other rule for integration. There isn't going to be a product or quotient rule equivalent. But if you do see a natural log of x in one of the problems here, when you have to integrate it, it's going to be with something else. It won't be by itself. Right, but just very quickly, kind of want to do quite a few problems just to practice and see every single one of these rules work. Right, the first one, I don't know why the integral signs are so small, but that's all right. The first one says, and they all have the directions, compute the following indefinite integrals, UC as the arbitrary constant. Now, for now, you can just think about them as integrals because we haven't seen what's called a definite integral. So indefinite integrals are just integrals for now. Now, if we want to integrate just a number, this is the rule 3 from above. So I'm actually going to go ahead and just write a number down for which rule we used in these steps of these problems. And for rule 3 here, it says if you integrate just a number, you get that number times your variable, which is x, plus c. But it does tell you use c as the arbitrary constant. If it said use k, if it said use f, if it said use something weird, weird letter, you would have to use that. But most often it's just c because that's the easiest thing to use. Right, but that's it. There's nothing else there. It's like when we do the derivative of a number and we get 0, it's just 0 and then you're done. Same thing here. Right, number 2. Number 2, we want to integrate 12x to the 5th dx. Now, like with derivatives, I'm going to do every step following one of the rules. Once you adapt to this and practice a lot, you might be able to skip some steps that aren't hard to skip. But the way our rules are set up is that you want the inside to be just a power of x or just e to the x to be able to do one of the integration rules. Right, so rules 3, 1 through, well, I guess just rules 1 and 2 tell you how to make the inside just like that. And rules 3, 4 through 6 say make the inside just e to the x or a power of x before trying to integrate. And you'll use rules 1 and 2 to get them in that form. Right? So here we don't have just a power of x inside because we have that 12. But what are we allowed to do with numbers is we're allowed to move them out with rule 1. So that's what I'm going to do. I'm going to first use rule 1 to move the numbers out. So we can move the 12 outside of the integral. And once we've done that, then we have only a power of x inside. So you will be able to use one of the rules to actually integrate it. Because you'll know with rules 1 and 2 here, if we don't get rid of integral signs, it's the rest of the rules that we actually do the integration. Right, but this here would be the power rule because we have x to a power that's not -1. And I labeled that as number 4. Okay. And what the power rule says, well, first off, we're going to leave that 12 out front. You don't have to write this big bracket or parentheses, but I'm just kind of separating since these are our first examples here. When we integrate using the power rule, what do we do? Like with the derivative rules, I recommend not memorizing the formula specifically, but what it says. We add 1 to the power, divide by the new power. So adding 1 to 5 gives us, I'm just going to do it out in the first one here. Oops. We got x to the 5 plus 1 power. We add 5 plus 1. Put that on the bottom. And now what I do here when I integrate, you can put the plus c anywhere. But what I like to do is just throw it on the very end. Because if you put it in this bracket, then it might look like you have to distribute the 12 through it. And you get 12 times c. But since c is just some unknown number, when you multiply it by 12, it's still just an unknown number. So just put the plus c at the very end. And we'll see a couple problems as well. When we have more than one integral to do, I'm just going to throw it at the very end of the last one. I'm not going to throw it in on all of them. Okay. All right, but once we're here, we integrated. Right, our integral is gone. Just simplify the 5 plus 1s to 6s, which you may have already done. And then because we can simplify the 12 over 6 to 2, that's all we're going to do. But once again, you'll probably get this quicker than you did with derivatives as well because the rules are very similar. It just takes practice because I know this section, we kind of learn all the rules at once, but the idea is all the rules are similar to what you've done before. Right. So the next couple here, really the only rules we haven't touched on. I mean, we did rules 1, 3, and 4 already, so you'll see rules 2, 5, and 6 as well. If there needs to be any algebraic simplification in problems, we'll see that as well. So number 3, we want to integrate 2 over 5 times t to the 8th minus 3 over 2 times t to the -4/3 dt. Now you will notice the letters match up. You won't see a dx with a t. They'll always match like that. But the first thing I would want to do here is do the integral of each part, just like when we had derivatives and we had more than one part. Right, and we called that rule 2 from above. So I got 2 over 5 times t to the 8th. After each integral, you do need to put a dt. So now that I'm splitting up my integral, I'm going to have 2 integrals with 2 dt's. Then we have a minus, and then the other integral has 3 over 2 t to the -4/3 dt. Okay, so this is using rule 2 here with a minus. Right, it just says if you're adding or subtracting two functions, you integrate each one, and then you put your dx, or for us in this problem, dt, in each one. So the way I like to think about it is the integral signs are paired off with the dt's. They're both necessary. Okay. All right, so we use rule 2 to break it up. Think of, back to our derivative rules and what we would do after we broke it up. We would move out any numbers that, any constants, because we wanted to use one of our rules, the power rule, the exponential rule, the logarithmic rule, and we still want to do that, right? As we outlined in the previous problem, the inside should only be, in this example, t to a power or e to the t. And so we need to move out coefficients. All right, so for the first one here, we got 2 over 5 to move out. And then the second one here, we got 3 over 2 to move out. We got 2 over 5. And then the integral, since the t to the 8th is in the bottom, make sure you write it as 1 over t to the 8th when you move it out. Definitely don't want to just move it to the top or get rid of the fraction. And then we move the 3 over 2 out. We got t to the negative 4/3 dt left inside that one. Okay. Now the second one is good to go for integration because it's just t to a power, which means we're fine. The first one, just like with derivatives, we have to take our rule very literally. If it's not t to the power, which it's not, we need to bring it up. So I'm going to do that and then just integrate both at once instead of doing one at a time. We need to bring it up to make just t to a power. Get rid of fraction. Right, and we've seen this rule a few times in this class now, so I won't go over it in detail. Just remember, when we bring the exponent, and when we bring something from the top to the bottom or vice versa, the exponent changes sign, so that this becomes t to the negative 8 power. We got that. All right, didn't do anything to the second one yet. And now the thing to point out here, I forgot to write my integral sign. That would definitely be confusing. The thing to point out here now is that the inside of each integral is just t to a power. Doesn't matter what the power is, it just is in the correct form, so we're going to use the power rule. And the one, you remember the one power that's special is -1, which we do not have. So we use the power rule for each. And I think we wrote that as rule 4. Let me just double check. Yep. So we're using rule 4 on both of them. All right, so we leave the 2 over 5 out front of the first one. Remember, we add 1 to the power. -8 plus 1 is -7. And we divide by the new power, -7, minus 3 over 2. Now, since this is a fraction, when we're adding 1, you had a lot of practice with subtracting 1. Adding 1 is the same idea, of course. But, just trying to do the first one in the calculator. -4/3 is our power. We want to add 1 to that. And if you want to change it to a fraction in your calculator, hit math, frac, and we get -1/3. Right? But if you write it out, just think about what we're doing. We're having -4, but since we're doing plus, we do +3 for the numerator. Whereas before, when we subtracted 1, we would do -3. So -4 plus 3 is -1 over our common denominator of 3. And then we're dividing by that new power. And then we got our plus c. Like I said, when I have multiple integrals, I just do 1 plus c at the end, because if you have 2 of them, it's still just a constant. Right? We don't know, what it is. If I have 1/2 and I multiply it by 2, it's 1. But if I have 1 and multiply it by 2, it's 2. So you don't want to try to overcomplicate that. Just add the plus c at the very end. I'm going to go ahead and box this in like I did before so it's easier to read. But when we integrated that, we got this. When we integrated the one with the fraction, just add 1 to the power and we got this. And now the last thing, this is typically the only added complication with doing the power rule for integrals is because you're dividing by the new power instead of multiplying by a power. If you divide by a fraction, just keep, change, flip it. The first one is fine. We have 2g to the negative 7 over negative 35, but I'm going to put the negative out front. That's my preference. Now when we do keep, change, flip here, we got 3 over 2 divided by negative 1/3. Remember, we changed the division to multiplication. We flip it, so it's 3 over negative 1. And then I have my t to the negative 1/3 there. And now the first one is fine. If you don't like negative exponents, you can bring it down and make it positive, but it's not necessary. Same reason as derivatives. Once you get the answer, you can simplify it, but we're not doing anything else with this problem, so don't worry about it. Second one here, the negative and negative will become a plus. We have 9 on the top, and 2 times 1 is 2 on the bottom. And we have t to the negative 1/3, and then our plus c. Now, I will intentionally say here that these number 3 and 4, are some of the last problems in the section. They are 2 of the hardest problems in the section. So when you work the homework, you won't see something like this right away. I know this uses a lot of our new rules pretty immediately, but not every problem is that difficult. A lot of them are actually more like the first two. Right, but this is something you have to do eventually in this section. All right, so the last one here, we have y cubed times e to the y minus 5y squared over y cubed dy, and we want to integrate that. So once again, this is why it's really important to kind of think about what should the inside be? What do we know how to integrate? Well, we know how to integrate. We need the inside to be, since we're dealing with y here for our letter e to the y, or a power of y. And this thing looks nothing like either of those. I mean, we do have an e to the y, we have a lot of powers of y, but we cannot have multiplication. Like I said, this is something that if we did the derivative of, like a y cubed over e to the y, we would do the power rule for. We can't have a fraction because we don't have a quotient rule. So we have to do one thing, and pretty much the only way to do this problem is to split up the fraction first. Now, I'll kind of reference why is that we don't have a quotient rule for integrals. So there's not going to be some equivalent. You need to get rid of fraction. And this is the easiest way for me to see how to do it. So what I mean by that is we write the first part, y cubed e to the y, over our denominator, y cubed. And then we also write the second part, 5y squared, over the denominator, y cubed. Right. But that's just algebra rule. We're not using any integral rules. But now that I'm in this portion here where I have each fraction separated, it's up to you how to simplify from here. There's a lot of things to do. Well, I mean, a lot of things you could do immediately. For example, here you can simplify each fraction because the y cubes on the left one cancel out. So that's what I'm actually going to do. All right, so the y cubes cancel out and the first fraction is just e to the y. That's really good because we need just an e to the y. Minus the 5 definitely doesn't do anything. And y squared over y cubed. Well, we have 2 y's on top and 3 on the bottom, so we can write that over y. The y's cancel, y squareds cancel, and we have our dy. That also helps a lot because this is set up like the previous one. Now what can we do? We can split it up into two integrals using rule 2. And then just like with derivatives, once you get more comfortable with this, you can kind of visualize, oh, I'm just going to do the derivative of each integral of each part, so that's okay. But just to show the complete details, when we split it up, we get our two integrals. And then the first one is actually just e to the y. So we can actually integrate that because it's just e to the y. The second one, we need to do one thing. And like with the previous one, I want to be able to integrate them both at the same step, so I'm going to wait. But we do have a number out inside the integral, and we want to move it out. Move the 5 out. Move out constants, coefficients, whatever you want to call them, using rule 1. So our first thing, we didn't have anything to move out. It's integral ready. The second one, we move the 5 out, and we get a 1 over y dy. And now this is the one where you don't have to change it to just power of y by bringing it up, because when we integrate 1 over y, that's the natural log. So the first one, oops, when we integrate e to the y, we get itself. So that's rule 5 from above, if you go ahead and have them written down and look at that. And then we have, in our second integral, we have minus 5, that stays out front. When we integrate 1 over y, we get the natural log of the absolute value of y. But that absolute value is important. Don't just write a parentheses. And that's rule 6. Right? But once again, when we integral, just do all your integrations and add the plus c on at the end. Now, if you did change this to a power of y, what would the power of y become? It would be -1. And that's the bad power that the power rule doesn't work for anyway. So that's a good trigger that you're using the other rule, the natural log rule. But once you're here, you're actually done. Right? We don't have anything to integrate. We don't have anything to simplify. We're good to go. Right? But like I said, not every problem is set up to be as indirect as this. But this problem specifically is really important as far as what you need to do to simplify before you integrate. You must, at this point, have the inside be e to the y or a power of y if your letter is y. You cannot do anything else at this point. All right, number 5 is just one that sort of like when we learned derivative rules and we only learned the power rule, we did not have the product rule. We acknowledged that you can still do the derivative. Same thing with integration. Okay, so we want to integrate 2x squared times 3 minus 4x. And once again, we do not have a product rule. We don't learn a product rule for integration. So what do we need to do to the inside to be able to integrate it? Well, we need to distribute. Right, so we want to distribute the 2x squared to the 3. That gives us 6x squared minus. Distribute the 2x squared to the 4x, and we get 8x cubed. Right, and the reason we have to do that is we can't split the integration up over multiplication. That's not a rule that we have above. And just like with derivatives, if it's not a rule, there's a reason it's not a rule, because you can't do it. But we can split it up over plus or minus, and after you distribute it, see what happens here. So now we use rule 2 to split it up. We integrate the first thing minus integrating the second thing. And then, once again, once you practice these enough, if you see how to kind of skip over these two rules, maybe a lot of people, you'll get to the point where you can just see this and integrate this. So you might be able to skip these two steps, but I'm going to just do that for all the problems in this section to really emphasize what we're doing. We can bring out the coefficients, bring out the numbers, bring out the constants, whatever you want to call them. There's nothing wrong with either of those names. So we have 6, integrate x squared dx, minus 8, integrate x cubed dx. And now the inside, just like from before, is just powers of x. So we can use the power rule because the power is not -1 in either of them. And again, the power rule for integration, we add 1 to the power, we get 3, and we divide by the new power. And then the integral of x cubed, we get x to the 4th, and divide by that new power of 4. We have our plus c at the end. And because I can actually simplify the numbers here, I'll do that. 6 over 3 is 2, so we get 2x cubed, minus 8 over 4 is also 2, so we get 2x to the 4th, plus c. And that is our integral. There's no reason to try to factor out anything here to simplify. This is plenty good, and especially when you deal with integrations, kind of as we saw here, since there's no rule for multiplying, if you factor something out and then you have to integrate it again, which that may or may not pop up at some point, but if you had to integrate again, then you'd have to integrate it like this anyway. So just leave it alone. Right, but the rest of the section is on computing what are called specific antiderivatives. Now, I will say once you learn how to compute the general antiderivatives from above, this is just one more step. What this is going to be is like if we wanted to do this last problem, if we were given the directions to compute a specific antiderivative, it would have to tell us something extra so that we could solve for C. That's the only difference. Okay, so computing specific antiderivatives means we will be solving for C. Right, the reason the general ones are called general ones is because C can be anything, so this isn't a set defined concrete function. When you solve for C, it's actually something that's very concrete. And that's all my directions here say. All right, so I just have a few problems here because they might word this with different notation. I want to make sure nothing's missed. Number 1 says compute C of x if C prime of x equals 5x squared minus 2 of x minus 2x and C of 0 equals 5,000. This is going to be the part that lets you solve for C. Even though we're not giving the integral notation, the first part is exactly asking us to do the integral. Figure out the function from its derivative. So if we weren't given this part, we would be doing stuff from last time. All right, so what I'm going to do is just put this on the back burner because we won't be able to solve for C until the end anyway, and just do this part. All right, so C of x, we want to integrate the derivative. We want to integrate 5x squared minus 2x dx. All right, once again, if you're comfortable with just integrating from here, by all means, do that. But I'm going to split it up. So we have two things here. I want to split up over the minus. We want to integrate 5x squared dx minus the integral of 2x dx. And I'm wanting just a power of x inside, so I want to bring out the 5 and the 2. We have the integral of 5 times the integral of x squared dx minus 2 times the integral of x dx. And now we have just powers of x inside. And there's not a special rule when x is to the 1 power. Like with derivatives, you just use the power rule. So we've got 5 when we, let me label that as number 4 here for our power rule. When we integrate x squared, we get x cubed over 3 minus 2. When we integrate x, that's like x to the 1 power. When we add 1 to 1, we get 2 and divide by 2, our new power. And then we add plus c. And so if you didn't have this plus c here, it would be impossible to solve for c. You wouldn't have it in your equation. That's why it's so important. But my preference with solving for z is simplify first. So the 5 over 3x squared, we can't really do anything with that because the 5 and 3 don't cancel out. Minus 2 over 2 cancels out, and we got minus x squared plus c. All right, so this is our simplified c of x. We integrated to get back to the original function. Now we need to solve for c. And I guess a little inconvenient that c of x is the name of our function and the constant, but that's why writing the of x part is so important. All right, so now we're going to use this part to solve for c. And what is this saying is we want to plug in 0 for x and set it equal to 5,000. Right, so we're kind of making our equation based on this. Otherwise, we just have this thing. But if you just follow those directions, so 5 over 3 in place of x is 0. Remember, you're not plugging in for c, you're solving for that. And then we set it equal to 5,000. What's nice about some of these, not all of them, but some of them, especially when you plug in zeros, a lot of things go away. And this is just 0, this is just 0. We have c equals 5,000. All right, but that is merely coincidental that this number here was c. It's not always going to be the case. But to finish up, you figured out c is 5,000, so we plug it in, and that's our answer. So c of x, our specific one is 5 over 3 x cubed minus x squared plus 5,000. Now do notice here that since we write plus c, when you get 5,000, it's plus 5,000. Some people, I guess, a little uneasy on, well, what if I get a negative sign here? Would it matter if I made it a minus c or something? If you did minus c instead of plus c, you would get c equals negative 5,000, and then the minuses would cancel out to give you that plus back. But if you just do plus c every single time, you're fine. You never need to do minus c, you never need to worry about plus or minus, just do plus c and then plug in the number you get. All right. So the last two I have here for this section are mainly because of the notations that it's written in. Otherwise, it's not any different. All right, so we want to compute r of t if its derivative is 93 over t to the 4th. And so once again, the first part is telling us to integrate the function 93 over t to the 4th dt, since that is our letter. And then at the end, to solve for c, we're going to plug in t equals 1, because since our variable is t, set it equal to 28, and solve for c. All right. I just like to mention that now that we know what this is used for, go ahead and point it out at the beginning. All right, so to integrate this, we don't have two terms, we only have one. We want to bring the 93 out front using our first rule. We got 1 over t to the 4th dt. Now, because this isn't 1 over t exactly, it doesn't matter if it's 1 over t to a power. If that power is not 1, you need to change it. All right, this is just an exponent rule, no derivative rules here. 1 over t to the 4th is the same thing as t to the negative 4. Change the sign on the exponent. And now here we can integrate it because it is just the power of t using the power rule. All right, so we got our t to the 4th, negative 4. We add 1 to that to get negative 3. Divide by the negative 3, the new power, and then add our plus c. And now, since this is one where you're plugging in something to solve for c, I mean, you might be most comfortable with changing that exponent back to a positive, but you could also just plug it in your calculator. But I'm still going to do what I said last time and simplify it a little bit. All right, so 93 over negative 3 works out perfectly to negative 31. And I'm just going to change it back to a positive exponent. So I'm going to bring the t to negative 3 down, and it becomes t cubed. All right, so the 93 over negative 3 become the 91, and the t cubed came from the t to negative 3 on top. Right. Now we can solve for c. And we do exactly what I wrote above, what it says to do. Plug in t equals 1. Set it equal to 28 and solve it for c. 1 cubed is 1, so this is just negative 31 over 1, which is negative 31, plus c equals 28. And you add the 31 to each side to get c by itself. And we have c equals 28 plus 31 is 59. Right, so all we do here, like last time, we figured out our c, plug it in, and that is our answer. I'm going to write the answer over here in all this empty space. So r of t equals negative 31 over t cubed plus c, which was 59. Right, but once again, same steps as last time, nothing special. All right, I think the last one might be the one that the way it's worded is most confusing. It says, find the equation of the curve that passes through the point 2, negative 62 if its slope is given by this derivative. Let me use that color, green color like I used, just keep it the same. All right, so this part here, the slope, they're giving you the derivative and we want the original equation, which means we want to integrate our derivative. All right, find the original equation from the derivative. Now the part here that's letting you solve for c can be a little more confusing because it doesn't have it written in the typical notation, but it is right here. All right, this is an x and y coordinate, negative 2 and negative 62. So what it's telling you, after we get to this point, we're going to plug in x equals negative 2, set it equal to negative 62 because that's what the y value is. and solve for C. All right, so to integrate this, we have two parts. I'm going to break it up, integrate the first part, and integrate the second part. Then I'm going to bring out the constants just like last time. So I'm going to bring out the 15 and integrate x squared. Then bring out the 12 and integrate x. And same thing as the previous two problems. This is just the power rule for each. We have a power of x inside, but it's not -1. So when we do the power rule for the first one, we get x cubed, add 1 to the power, and divide by the new power, minus 12. And then when we integrate x, that's x to the 1 power. So we get x squared, add 1 to that power, divide by the new power, and then add c at the end. And then once again, same thing as before, just simplify. 15 over 3 becomes 5, so that works out quite well. 12 over 2 becomes 6, that also works quite well. So this is our function not solved for C. And now we can solve for C. So we plug in x equals -2. And we set it equal to -62. And then solve that for C. All right, so -2 cubed is -8 times 5 is -40. Minus -2 squared is 4 times 6 is 24. -4 minus 24 is -64. And then add the 64 to each side, and we get C equals 2. So we have our function here. We use the point it told us to use to solve for C. And then we plug that in for our answer. Since it's talking about y and x, you could write like f of x or y or something. Y equals 5x squared, or sorry, 5x cubed minus 6x squared plus 2. Okay. All right, so the last one is also an specific antiderivative, but it's in a word problem. Just kind of like show you right away that word problems dealing with antiderivatives is actually a very common thing. I would actually not be too surprised to say that if you were interested, if you are one of those people that is likely to do calculus in whatever business field you go into, you'll probably integrate more than you do derivatives. Because the integrals, as we'll see in the end of this chapter, tell you a lot more, and things that are more of interest for business, at least. All right, so number 4 here, it says the monthly sales of a particular personal computer are expected to decline at the rate s prime of t equals -30t to the 2/3. So they're giving us the derivative, and they told us rate anyway. So, either one of these is saying they're giving us the derivative. If we're given the derivative, we're probably going to integrate it, especially if we're in this section. The company plans to stop manufacturing this computer when monthly sales reach 500 computers. So what it's probably going to be asking us at the end is, how long will it take to reach 500 computers? Then they'll stop manufacturing them. If monthly sales now at t equals 0 are 1,940 computers, find s of t. Right, so this is pretty much going to be, at this point, a problem like before. And then, the real question that we want to answer is how long will the company continue to manufacture this computer? All right, so the blue part is asking us to find S of t, and they're actually giving us a way to solve for C here. We're gonna, once we get to that point, we're gonna plug in t equals 0 and set it equal to 1,940. Right, but we got to start by doing the integral of our derivative to get back to the original function. We got to integrate -30 t to the 2/3 dt. Just like we've been doing all section. And bring the -30 out front. Right, it's only one term, so we don't have to break it apart otherwise. And now this is the inside is just a power of t. The power is not -1, so we use the power rule. We add 1 to the power. 2/3 plus 1 is 5/3 because we do 2 plus 3, which is 5. We divide by the new 5/3. That's our power rule, our rule 4. Plus c. Don't forget, we're integrating. We have to write the plus c. And then we did one other example before where we had a fraction from division. So you do want to simplify this, especially with solving for c. And I'm going to go ahead and simplify it to keep, change, flip. So the fraction changes to multiplication, and we flip to 3/5. I'm just simplifying. And then -30 and 5 cancel to give you -6 times 3 is -18. So this is our S of t without solving for c, just like from before. Now we're going to solve for c. So we take our function here, we plug in t equals 0. So we get -18 times 0 to the 5/3 plus c, and we set it equal to 1,940. Now, once again, plugging in 0 is great because when we do that, 0 to any positive power is 0. And that's just makes getting c very quick because that is 0. We got c equals 1,940. But once again, we saw previous examples where c is not just that number, so be careful. You do almost always have to be plugging in t equals 0. And even if you do, it might not be that. So just see the way it works out. But we plug in our c, and then we have our S of t equals -18 t to the 5/3 plus 1,940. That's the first part. The second part asks, how long will the company continue to manufacture this computer? Well, it says they'll stop manufacturing this computer when monthly sales reach 500 computers. So what we should do is, now that we have a formula for the sales, set that formula equal to 0, or sorry, set it equal to the 500. That'll give us how long it takes. That'll give us the t value for when it hits 500 sales. And we'll be able to solve for t. All right, so let's go ahead and do that. We got 500 equals -18 t to the 5/3 plus 1,940. Subtract that 1,940. 500 minus 1,940 is -1440 equals -18 t to the 5/3. Now to continue solving for t here, you want to get rid of that -18 first. And I think this works out to a perfect number, but I just want to make sure. -1,440 divided by -18. is 80. So we got 80 equals t to the 5/3. Now to solve for t here, you can do one step. If you raise each side to the reciprocal power, raise each side what happens is the powers on the right will cancel, and then we'll just be able to compute it on the left. So what I mean is if we raise each side to the reciprocal of this 5/3 power, which is 3/5, would help if I actually wrote 3/5 instead of 5/3 again. Right, the reason this works is because the exponent rule here says you multiply them. And when you multiply 5/3 times 3/5, they cancel. That's why we do that. So we've got t equals 80 to the 3/5 power. Now this is not probably going to be a nice number, so just put it in your calculator. 80 raised to the, and if you want to be super careful, make sure you put your power in an exponent form, 3/5, and you get 13.86. So it'll take about 13.86 months for them to stop producing this computer. Right, it doesn't say how long to round. I mean, typically, I guess we're talking about months. We'd probably round to 14, but just take a look at what the problem says specifically. All right, but that's the kind of problem where integration is used. Very often, as weird as it seems when you're studying things in nature, well, I guess more so business for you all, as odd as it is, you can figure out the rate of change or the derivative more easily than the actual function itself, because you just study how things change instead of the whole numbers themselves, and then you go from there. Right, so that's why integration is so important. Right, but that is the intro to integration.